Okay, so I'm Aviral and I just completed my foundational year right now and I'm doing my bachelor's in computer science and I'm in currently second year. So today I'm going to talk about fractals. Hmm. So let's move to the contents. So I'm going to discuss about the recursive patterns. The recursive patterns are basically a characteristic of fractal. And then I'm going to discuss about the coast of India paradox. And then I'm going to discuss about how do you imagine a fractional dimension and how are complex functions that are of complex number related to the fractal. And at last, I'm going to discuss about how is Minecraft connected to fractals. So without any further ado, let's get started. So the first question is, what does a smartphone and snowflakes have in common? So the answer is fractals. So how it is in common, I will just tell in a few slides. So you can just think about it in the meanwhile. So first I will discuss about what are fractals. So the fractals have some things in common. So one is they are never ending patterns and those are infinitely complex patterns. And even if you try to zoom in inside a fractal, you will see the similar kind of shapes. So if you try to see or if you try to zoom at different scales, so you will see the self-repeating kind of pattern or recursive pattern, and that is basically a fractal. So there's an example of fractal. This is called Sierpinski triangle. So as you can see, there's a triangles inside of triangles, and inside of triangle there are like it's like a never-ending pattern, and it's infinitely complex. So this is one example of fractals. But the fractals are also found in nature. So I'm going to discuss about that soon. So first, we're going to discuss about the coast of India paradox. So this is a paradox. So this is a situation in which I just want to find out the parameter of the coast of India. So I just want to measure the coast of India and want to find out the parameter of this. So what I will do is I will just try to map it by putting the dots, by connecting the dots, and I will get a rough estimate, just a rough estimate of the parameter. But this is not the exact parameter of the coast of India. So what I will do is I will do it one more time and make it a bit more accurate, but it isn't that much accurate. And I can do it so on and so forth, and I can try to measure the each molecules, but that's not possible. So what it turns out that is the parameter can be infinite, because if I try to measure the molecules or the oceans and the beaches, it's like it's very complex. So this is also called the coastline paradox, and it is like people saw it as the coast of Great Britain, but I just saw it as the coast of India because it's familiar. So now the fractals are omnipresent in nature. The fractals are everywhere. So this is a fractal. This is a computer generated image of fractal. So it's kind of similar to the nature. As you can see, this is similar to a shell. It because it have a recurring pattern to it. It is also similar to a hurricane. And there's one more type of fractal. This is a branching fractal. So what is this? There is like recurring patterns of branches. You can see as in this GIF file. And if you try to zoom in, you will see more and more branches. So this type of branching fractals is much more common in nature. You can see all around us. In trees, you can see the branches of the trees, or you can see the courses of rivers, the branching of thunderstrikes, or even you can see inside your own body, like the nervous system or the neurons going flowing inside your brain. So you can see this branching fractal pattern all around us. But why the nature is like has a fractal pattern? Like why is it important? So I'm just gonna go back to the previous question that I asked at the start of the slide that how are snowflakes and smartphones related? So as you can see, snowflakes are natural fractals. You can see a similar self-repeating pattern in a snowflake, and if we try to use this pattern, it's gonna make the antenna much more efficient. So in earlier days, we used the big, and we used to have big antennas to tune into radio signals, to tune into TV signals. But in today's world, we just use our smartphones, and they are able to, like, the smartphones somehow able to receive all those information, all those radio wave signals, and mm, and this is only possible because of the fractal antenna that are present in the smartphone. So in today's smartphones, we use a fractal antenna which is called which is made up of Sierpinski square. So instead of having a snowflake like this, in today's world we use a self-repeating pattern of planes. Maybe I can just show you. So we use this type of pattern, but this is a 3D. This is in 3D space. We use this type of Sierpinski carpet in today's world. That is like very useful and very efficient in taking out the receiving the radio signals. So So now I'm going to discuss about fractional dimension. So you might have have a basic understanding of dimension right now. You know what is 1D, what is 2D, what is 3D, but and n times. But what if I want to discuss about 2.73D or something like a fraction? So you can imagine a banana, like I gave you 3 bananas, but can you imagine I have to give you 2.73 bananas? So that's where the concept of fractional dimension comes in, or fractal dimension. So how can we define a dimension by just looking at the shapes? So how can you define that? Okay, this is a square, this is 2D. So what we do is, like, this is a line, so we're just gonna subdivide it, all the shapes. So if it is line, I'm just gonna subdivide it, so it's gonna break into 2 lines. And if I subdivide the square, it's gonna break into 4 parts, and the cube similarly will have 8 parts. And this Sierpinski triangle, this is a fractal, which will have 3 parts. So if I want to so this part of the line is the half of it. This is 1/4, this is 1/8, and this is 1/3. So if I try to generalize the concept of dimension, so it's gonna look like this. So if I try to use the half as a scaling factor, and to the power like 1. So if the power is 1, it's a 1D. If the power is 2, it's the 2D, and if it's 3, it's the third dimension space. So that's how we can calculate the dimension of a fractal. So if I want to calculate the dimension of a fractal, I'm just gonna use this. I just have to find this question mark. So how do I find this question mark? I will just put it is equal to 1 by 3, and with the help of logarithms, I will get the dimension as 1.586. So that is the dimension of a fractal, which is a subconcentric triangle. But why is it important? Why, like, what is the use of it? It should be useful if I'm just um, making a concept of fractional dimension. So in the nature, as we can see, like, we don't have perfect shapes. So we don't have a perfect squares everywhere. We don't have perfect cubes. We have uh, kind of fractals. So if I want to define a dimension of an ocean, which is calm, the dimension turns out to be 2.05. And if it's violent, it turns out to be 2.3. So the nature is not in like integral dimension values. It have fractional dimension values. So now I'm going to talk about what is this? This is a complex number, but what is the role of complex number in a fractal? So this is called a Mandelbrot set. It is given by Benoit Mandelbrot. But so why this Mandelbrot set is important? So so I'm just going to show you. So this is a simulation of a Mandelbrot set. So as you can see, this is a Mandelbrot set. So what is it exactly? So it is a mapping of the function it is a mapping of the function which is z square plus c, where z is a complex number. As we all know, a complex number, if z is a complex number, it has components. It has a real component and an imaginary component, a plus ib, and where c is an arbitrary value. And if we want to just plot this function, so what we will do is, if we just plot this function and put y-axis as an imaginary plane and real, and x-axis as a real, as a real number. So if we try to plot this, we will get this type of Mandelbrot set pattern. And what is interesting about this, because this is a mathematical pattern, but this doesn't have this. If you try to zoom in, it is it is like self-replicating. So I'm trying to zoom in. So as you can see, the similar pattern is emerging. So it is taking time to load because it all depends on the processing power of your computer. So if I try to zoom in more and more, I'm seeing the similar type of pattern. So now I'm going to talk about how it is calculated. So how do we plot this, and how can you make our own Mandelbrot set simulation? So if we have this function and we're gonna put 0 at first, we're gonna start with 0, but we're going to change the c values. So the c value is an arbitrary value. So first we're going to put 1 here. So we're going to see if we're going to put 1, and we're going to use a function of 0. So if we try to put the value of 0 in z plus 1, we get 1. And then we put this 1 back in the function, we get 1 square plus 1 is 2, and so on and so forth. You see this, there is a series, it goes to infinity. So we don't get anything out of it. It's just going to infinite. Uh, so what?
What happened?
Just a minute.
No problem.
Oh yeah.
She likes teaching, right?
Yes.
Okay. So it is the, if I put the c is equal to 1, it's going to infinite. But what if I put c is equal to minus 1? So what if if I put c is equal to minus 1, and I'm just doing starting from 0, the answer, so 0 plus minus 1 is equal to minus 1, and if I put it back to the function, it comes back to 0. So it's always coming back to 0, minus 1, 0. It's repeating, it's kind of bounded in this thing. It's not going to infinity. So if it's not going to infinity, it comes under the Mandelbrot set. So now I'm going to show you the I'm just going to show you this thing first. So as you can see, if I want to make a simulation of Mandelbrot set, what I will do is, if the c value is going to infinity, it's coming out of the set, and if it's less than or equal to 2, it's inside the set. So if I put this statement inside the computer, I will generate this type of graph, and this is known as Mandelbrot set. So back to the simulation again. So as you can see, just reset it. So all the black part, so all, if the part is black, that means it is a boundary, it is a bounded condition. So it is not going to infinity. But if you see there's something, there's like a colored pattern to it. So that shows like the color, the different color shows that how fast the function is going to infinity. So as you can see, the color near the Mandelbrot set is a kind of different. So that means it's going at a slower rate to infinity than the numbers that are outside this area. And by this you can get an infinite amount of fractal pattern. So I'm gonna so here we go. So now I'm going to talk about why is Minecraft coming to the picture here. So Minecraft is a game which uses procedural generation. So without using the procedural generation, how can like a 300 MB game contain store a map, a huge map of 3.6 billion square kilometers? So and if you try to reload the game, the map will always be different. It always generate a new seed, the map will always generate, and it will generate the different type of biomes according to the random seed. And if you try to store all this without using the procedural generation technique, it's gonna be humongous, and I don't think you will be able to store it in your computer. So procedural generation, it is a method of creating data algorithmically. So instead of doing it manually, you are just putting an algorithm. So it is kind of algorithm is kind of a recursive algorithm, that is a fractal based algorithm. So we are using this to make to procedurally generate the whole environment, and it tremendously save time, and it is used in animation movies. Like if you want to animate, if you want to put a tree or if you want to put a lot of trees, you have to get a detailed view of all the branches. But with the technique of procedural generation, we can put a small algorithm, and it will do it on your own instead of doing it manually, which will take a lot of time. I don't think how much. So So after this session, I want you to look up, if you are interested looking more about fractals, I want to you can just go through all these topics that are interesting and that are about fractals. And there are some important YouTube videos. You can just scan the QR code to see all these YouTube videos. So I'll just wait a sec for you to take a screenshot of it. And yeah, like okay, that's it for my session, and thank you for all your time. So fractals are basically everywhere in the nature. We just need to look around, and maybe you will see nature in a different way. Thank you.
Any questions?
I have a question. Based on the dimension of ocean, do you model waves differently? Are there any applications like that?
Yeah, like with the dimension, I think you can model and in animation you can use this kind of dimension behavior and model a wave, like because it can also help in the chaos theory. You can like there's also like a concept of, I just put it in the things that you have to research about fractal noise, fractal Brownian motion. So it can help you generate the randomness of the ocean with the help of dimension, fractional dimension.
Any other questions?
Oh
Okay.
yeah, I will just share the slide.
Yeah, you can share in the chat box.
Mhm.
Okay.
Yeah. Okay. Thank you, everyone.
Yeah. Thanks, Avira.